Hey, you haven't had a podcast from me for a few days. I always feel a little bit badly doing these because I know you're all working really hard, but uh, this has been a complaint of mine, if I can use that word, already a little bit of a negative connotation, that so many students get involved in BSc and don't know, the basics of the different systems in the satellite. Okay, well, you can say, you're a software person or you're a digital hardware person or whatever it is you're doing, and maybe you don't care, how structures work, how thermal works. The trouble with that is it kind of runs counter to the philosophy of Brown in general. And everyone, and I know some of the people in this class, have stories about how they studied X in school and then they ended up doing Y and Z and never did X in their real life. That was my story. I never studied satellite engineering anyplace, to tell you the truth. And I became this satellite systems engineer. And, I've had students and employees with all kinds of crazy stories. So, it pays to know a little bit about a lot as well as a lot about a little bit. I'm not saying 176 is a balanced diet either, but it's one of the few courses in the whole wide world where you can get a little taste of everything, and as my boss here in Rome says, get the rules of thumb, which is, super important in that it gives you the intuitive part. The intuitive part, is pretty important because at least you can tell you're never going to be doing everything, but a lot of people are going to be telling you, like I'm doing now, reviewing, this lunar robot thing, and now next week I'm working for NASA, working on a solar sail and a whole bunch of other things. And you have to have some way to latch onto it and to say, well, is all this really making sense? Or, is this a little bit crazy? Or what? It isn't even to make a judgment. It's to be able to ask the question. And also, when you work on a small program, and we'll get into this in the management podcast, a small program is not like a big program where you work in the thermal engineering department and there's 100 people in that department and you get assigned, which of the, multi-layer insulation should we use on the outside of this box. I had one of my students from 176 went to work for General Motors and ended up working in multi-speed automatic transmissions. And, she had never, she wasn't an automotive person or anything like that. And, she was working in a very, very narrowly defined niche. And small satellites are not like General Motors. You've got, like you guys, you got 10, 12 people, and everybody has to have some sensitivity to what's happening with the other people. You can't just, well, I'm focusing on the processor and I don't care, because the processor is going to generate heat, it's going to need power. What comes into the processor is going to be a function of what's going, whether it has to manage the power system and what that means in terms of how often it has to look. And it just pays to have a general idea of what's going on in the system as a whole, even to do a niche job within that system very well. And not every engineer agrees with me about that. But anyway, that's kind of a Brown way of thinking, I have to say. And it's one of the reasons that I came back to Brown. So, everybody's got their point of view, but that's my point of view. So I'm kind of, I have to say, imposing it on you. And I think most students appreciate it when they go out in the world that, you do tend to get hyper specialized, especially at the beginning of your career. And so, the university environment gives you the one opportunity you've got to see the big picture before, that happens to you. So, anyway, let me dive into power. Slide 1 is the homework, which I thought is maybe a good way to start the chapter off because, you want to, okay, these are the questions that I need to answer. It kind of focuses your listening. What are the operating modes? And, it mentions a power spreadsheet, so I'm going to put a power calculation spreadsheet, though you're already doing something like that. But I'll give you mine in the resources section of Canvas files, resources. And of course, getting the size of the solar panels and the mass of the battery is kind of the answer, right? At the end of the day, what the system designer needs to know is how many square meters and how many kilograms of lithium-ion batteries. It kind of all those calculations boil down to two numbers. But I mean, that's the way it is. You're going to hang a swing set from a bolt. Well, is it a 1/4 inch bolt, or is it a 1/2 inch bolt, or is it 2 1/4 inch bolts? I mean, the answer is fairly trivial, but the calculation that goes into getting that answer may not be so trivial. And the end of mission has to do with the fact that things degrade. And of course, there's a big philosophy in aerospace that you've got to design for the end of mission, which I'm actually not as, I don't subscribe to that philosophy. And I live on the edge a little bit, as you are doing. If you live working in small satellites, you don't have the luxury of having all the margins and everything is 150%, if not 400%. That's a NASA world that is slowly disappearing, because while you can't say that it's better to not have that margin, you have to look at an even bigger picture, which is, if I tell NASA that my project is $20 million instead of $2 million, my first project we bid at 5% of what the major aerospace companies were saying it was going to cost, 10%, let's say. So if I go to NASA and say I need $20 million instead of $2 million, that means there's 9 other people who could do something with $2 million who aren't going to get that opportunity. So yeah, it's fantastic. You get all this money so that you can sleep well at night, but you shouldn't sleep well at night because you wiped out 9 other equally valuable ideas to do yours. And, that's not the way the space world is working anymore. The space world is becoming much more diverse with many, many people. That's the way the biological world works. We only have one heart. If it fails, you're dead. But there's 7 billion people in the world. Humanity, as our DNA, does not care if you die. I don't want to come off like Bolsonaro, but, even Iridium said, no, it wasn't Iridium, it was Globalstar, one of the early constellations. And I told this story when one of their satellites actually failed on orbit. And their response, what are you going to do about that? What are you going to do differently in your new satellite so they don't fail on orbit? And the program manager said absolutely nothing. It was designed so that occasionally they would fail on orbit, because we have to launch a lot of satellites and they can't be all 200% reliable. So, that philosophy takes you down to, am I going to oversize everything so that on the very last day of a mission, I have 100% of everything still running? Well, if you're a geosynchronous satellite, maybe you do that because you're guaranteeing the customer 300 channels of HDTV for 17 years. You have to show them that on day 365 of year 17, or year 16 in that case, you've still got enough power to run all those transponders, even though that the television standards and everything else are going to change, and that satellite's probably going to get resold to some, second or third world country willing to live with an old technology for a low cost, and that the customer is not going to really care anymore. But anyway, we'll talk about that in more detail. Okay, slide 2. Slide 2 is all about aperture. There's only one sun. It only puts out 1,300 and whatever it is. I hear numbers, 1,343, 1,350, 1,370 was in another NASA proposal I read. I have no idea where these numbers come from and why they change, other than maybe I didn't realize the sun's output changed that much. Tens of watts per square meter is a pretty big change. But, I use 1,343. Whatever it is, you can't make any more power than you've got aperture. It's all about aperture. So there are other apertures, right? The number one aperture, this is really the number one aperture, because we haven't talked about radios yet. But the number 1 or 2, the other aperture, is antenna, right? The bigger your antenna is, the more directional it is, the more bits you can get down because your signal is stronger. So, we'll get into that. Then there's also a number 3 aperture, which is not true of every mission, but if you're doing imaging, the size of your optic. The bigger the optic is, the more resolution power you have because of the diffraction limit. Not that we ever get to the diffraction limit, but it's a boundary. And if your optic is small, there's only so much resolution you can get in terms of angle, and that boils down to dimensional resolution, depending on what distance you are. And but another problem with small apertures is small light gathering. And as your light gathering goes down, it's like radio. Your noise becomes greater relative to your signal. And as you know from taking pictures with your smartphone in the dark, a lot of noise, because they turn the gain way up to see the light that is there, and that brings a lot of noise bits visible in what would have otherwise been black pixels. So there are three apertures that drive, satellite design. And, there are three major considerations. And number three, I left in category number three because not every satellite is an imaging satellite. So that one is not, but every satellite except ours has solar panels, and every satellite except the moon has an antenna. All the, human-made satellites, synthetic satellites, are, have antennas. So, well, yeah, even Echo had an antenna. Okay, so the picture is of a design that I think we did it in class, or I did it on my own. There was a PhD thesis written at MIT about how to print solar panels from a roll of mylar with a bunch of, aluminized mylar, with a bunch of fairly caustic, like chemicals on board. And I did the calculation. If you had a cubic meter satellite, you'd have enough chemicals on board to at least roll out 4 solar panels, 1 by 20 meters. That's a huge aperture, and even though they have low efficiency in terms of watts of electricity per 1,343 watt per square meter exposed to the sun, their efficiency was 10% or something like that. But still, with 80 square meters is unbelievable. And it just amazes me that in all these years we are still going to space with the solar panels already manufactured, and they're super fragile, and they're under cover glass, and they have to be deployed, and they weigh a ton, and they're very expensive. And it's like, what are we doing? There are things that NASA does not look at. And I mean, they do look at this a little bit, but not in a serious way, like we've got to master this. It's in a way like, well, this is an interesting research project, and we'll throw a little bit of money at a college professor somewhere. But it isn't exactly, World War III, if you know what I mean. So, I'm always looking at things that are not happening and asking why not. That's what Space Horizons is all about. And this is one of the things I'm always wondering, why the hell are we, building solar panels as, I call them paddles, the mechanical structure behind nowadays usually carbon epoxy plates, because the solar panels are rigid, and if they flex, they're going to break. And so you have to have a really rigid structure, but really rigid structures with lots of surface area tend to be what I think of as snare drums, as drums. And so they vibrate. And so the launch loads couple into them really well. So then you have to stiffen them in order to get their resonant frequency up. And it's a kludge. It's a super kludge. And then we build these things to undergo, to sustain themselves under enormous launch, DC loads, the accelerative load of the, launch vehicle accelerating. And even worse, the accelerative load, you can handle that. But the other part, the vibration load, is much harder to accept when you have fragile, very rigid glass-like structures. Okay, on to slide 3, doing some numbers. This is a classic back of the envelope, calculation that I love this calculation. So just bear with me here. You can probably read it much faster than I can say it. But it's a good example of, how far reality diverges from specifications when you're doing engineering. I feel like, if I had to make 99 slides that every engineer should see in their life, think of how many thousands and thousands of slides we all see. I did this review for NASA. There were, in 2 days, we went through 280 slides. So you go through a lot of slides in your life. And so 99 sounds like a lot of slides, but hey, in this class, we do a lot more than 99. Okay, so you start off with, you can see I used a different number here, 1360 watts of solar energy per square meter. It's like, wow, I have no power problems, right? 1 square meter is, about the area that you would project, dressed, standing outside. Okay, so it doesn't seem very hard to get a square meter of aperture. Okay, on a CubeSat, yes, that would be big. But on on any other satellite, so on a CubeSat, we'd be at a lower number, something like 10%, 5% of that number. But even 1% of that number is 13 watts. I'd settle for that on a CubeSat. So 1% being 10 by 10, right? So 10 by 10 centimeters, we should be able to get almost 14 watts out of that. And, if we're a 3U cube, we'd be at 3 times 14 watts, which I think is 42 watts. That's like big power compared to what we really get. Okay, the trouble is the solar panels, how efficient are they? Well, you hear all kinds of numbers. If you build them, if you buy them from, if you buy silicon, you're going to get 8%. If you buy gallium arsenide, you're going to get higher numbers, which are going to quote to you between 20 and 38%. Are you, as a small, low-cost satellite designer, going to be able to get the same quality of gallium arsenide as the big manufacturers who are, who knows? So, plus they do degrade over time, and not all of them are going to work, and I don't know. Let's use 24% used to be a number that people would have died for. Now it's a number that's considered pretty mediocre, but let's use it as a working number for cheap satellites where you're going to be begging for low-cost, solar panels, with the caveat that if you're working on a major program, you're going to be able to do in the low 30s, probably. Okay, the trouble is, at the end of life, if you're talking many years in polar orbit, which is all the Starlink satellites, right? Many, many satellites are in polar orbit. I personally hate it for many reasons. One reason I hate it is the radiation problems are such a hassle. Another reason I hate it is that the satellite is wasting most of its time going over the North Pole and the South Pole where there are no customers. So it makes much more sense for most services to put them in a 57-degree orbit because 90% or more of the world's population lives between plus 57 and minus 57. And the hell with, seeing what's going on the North Pole. Do I really need a satellite that sees the North Pole every 95 minutes? The logic of that, doesn't do it for me. But there are reasons when we talk about orbits, there are reasons. Anyway, you're in a high radiation environment, probably. If you're a geosynchronous, you're in equatorial orbit at 39,000 kilometers. You're outside the magnetic field of the Earth, way outside. So you're in, the full space radiation environment and the solar, particle flux and everything else. So you're going to see significant degradation, which means that square meter that we used to have 1360 watts, we're now down to, not quite 10%, but not 15%. We're way down from where it was. Then if you're in low Earth orbit, you're only in the sun 60% of the time. Then you're in the shade of the Earth. So your square meter, if you orbit average it, is giving you 120 watts. So now we're below 10%. Okay? Then are you really pointing those solar panels exactly at the sun, or are you taking a cosine loss? So assuming you're taking some kind of cosine loss, to be generous, because maybe you've got a point to camera. Maybe you've got a lot of other things going on in your life. Maybe your gravity gradient stabilized, your aerodynamics stabilized. Unless your sun stabilized, pointing at the sun, and your customer is willing to accept that pointing, or you spend a ton of money to manipulate your solar panels like the space station does and, geosynchronous satellites do, with actuators and motors and algorithms and all the disturbances that are going to cause, those are going to cause to your attitude control system, you're going to be off of the sun line. And so let's just pick a number, we'll go down 20%, less than 20% to 100 watts. Then one of the things that people forget is that solar panel efficiency is quoted at room temperature, like 20 degrees C, 20 Celsius. So when real solar panels get hot in the sun, just when you need them, they're hot. And the hotter they are, the less efficient they are. So it depends how hot you let them get. If you're worried about the solar panels radiating back onto your satellite and heating the satellite up, and you insulate the back of them, which is what this lunar rover did, the solar panels are going to get super hot because they're black virtually on the front. So the front radiates back to the sun, but it's also absorbing very efficiently, and the back's not radiating at all. So 25% loss in efficiency is not unusual. It's pretty much standard. So even though the solar panels are quoted at 24%, they're really more like 20% because when you're using them, they'll be hot. Okay, then what are you doing with the solar panels, right? They put out a DC voltage that'll be 50 volts or 70 volts, and really it's not a fixed number. It's all over the map, depending on what their temperature is, what their sun angle is, whether some of the solar panels happen to be shadowed by an antenna, how many panels are in how much sun, because if they're wrapped around the satellite, they'll each have their own exposure angle. They'll each be, so you have a varying DC voltage source, which is not at the voltage that you want. So you've got to do DC to DC conversion, and that's not efficient, right? Particularly when you have to constantly be varying that voltage. So the solar panels at any given current draw, any given power draw that you have, will have a point of loading them. It's like an impedance matching problem. If you try to draw too much current out of them, their voltage will drop, so the net power will be lower. If you try to not draw too much current from them, yes, the voltage will rise, but you'll lose more in current. So there's a magic point. Exactly what voltage do you want to match them at to get the maximum power? We call that power point tracking. And all modern power systems have a power point tracker that's constantly deciding what impedance to put across the solar panels, what load, to get the maximum power transferred. That will be at some random voltage that then needs to be converted to one or more voltages that you use in your satellite. One of the main draws of solar power is recharging the batteries from the 40% of the time you're in the dark. Or because when you do an operation, you're using a lot of power, and then when you're not doing that operation, you're recharging the batteries. So batteries need to be charged at a certain voltage, particularly lithium-ion batteries, but that voltage depends on the temperature that the battery is at and its level of charge. So you've got all these different voltage adjustments going on. So a simple DC to DC converter is not going to cut it. You need a computer-controlled voltage converter, and those are not efficient, And then the batteries themselves are thermodynamic devices. They're not 100% efficient. When you charge batteries, they get warm. That's waste heat. When you discharge batteries, they get warm. That is waste heat. So batteries have what we call an internal resistance, which is kind of a model for how much power is being dissipated inside the battery. So I put that number down at 85%. Frankly, if I were going to remake this slide, I would probably make it lower because I've put together two different effects together on that line. One being DC to DC conversion inefficiencies and the power point tracking, which is never exactly perfect to get the maximum power out of the solar panel that the manufacturer told you. And, power point tracking is one problem, and then charge-discharge efficiencies into and out of the batteries is another problem. And those numbers are kind of like 80. Just the battery is going to, at least dissipate 10% of what you put in as heat, and then 10% more. So I think this number is way too optimistic. But let's just say we get 55 watts net charged battery out of the 1360 watts that we thought we were intercepting from a square meter of sun. Okay, let's say you have a meter. Let's say you just have a plain old flat panel, solar panel, and it's 1 meter on a side. Can you put a meter of photovoltaics on that? No. That's one of the little lies of the solar panel world. Yeah, they quote you a gallium arsenide, 38% efficiency. But that's 38% efficiency of the gallium arsenide. What's the efficiency of the wire traces between the sheets of gallium arsenide, of the little outlines of it's a tile. And you have to put a lot of tiles down on that square meter, and there's grout between the tiles, and grout being the wiring and everything else. So can you put a square meter of photovoltaics on a square meter of paddle? That's why I have this word, paddle. Paddle is the mechanical thing that holds and then the panel is the actual photovoltaic integrated onto it. If you have a square meter of paddle, you don't have a square meter of panel, and 80% would be pretty good. So you lost another 20%. Compared to your geometric area, your actual gallium arsenide or silicon area. Okay, it's very hard to guesstimate shadowing. But there's more to well, the trouble with shadowing is if you have a string of solar panels, string of tiles that together give you 50 volts, if you shade even one of them, it shuts that string down. So it's a little nonlinear. It's either on or it's off. And how many of those strings are on or off depends on if you've got a gravity gradient boom, if you've got other deployed objects sticking out of the satellite. You'd have to do a very detailed mission analysis to know how often and how much every deployable is going to have an effect of shadowing how many strings, which mostly we never do that analysis. We just take certain special cases. It's hard to guesstimate it. But, I put it down for, other 10 to 15%, let's say. Then there's another problem, which is the cosine loss that we talked about is not really a cosine. When you get down to a shallow angle, in other words, let's say you have a CubeSat, and neither face of the CubeSat, all the faces of the CubeSat are covered with solar panels. Neither face of the CubeSat is totally pointing at the sun. One has got, a certain angle, and the other's got the rest, right? But if the one that's got the rest is a shallower angle than about 30 degrees, nothing will get into it. So it's like a cosine effect when you're near perpendicular. As you come off of perpendicular, the reflection becomes a bigger and bigger issue until at an angle, it's like looking up from the bottom of a swimming pool. You dive down a meter depth and look up, you can see the ceiling of the pool, the pool building, the natatorium, perfectly. But you can't see the stands because they're off to the side, and at that grazing angle, the water surface to the air, reflects the light back at you, and all you see is water. So you have a circle above you. When you're scuba diving, you always see this. There's a circle above you where you can see sunlight, even if you're very, very deep. But off of that center, you see nothing. So your solar panels are kind of underwater. They're underneath glass. They have their own surface properties. And so in some way, that's going to wipe you out because you're not going to have the total cosine working for you. And that means any solar panels that are at a grazing angle to the sun are basically not doing anything. When you add all those together, you're at 30 watts, and your net real efficiency of making usable electricity from that 1360 watts is 2.2%. That's less than 10% of the... So the solar panel efficiency, it's all in series. Every one of those numbers counts, but they don't tell the whole story. The solar panels, if they were 30% efficient, your real efficiency would be 3%, roughly, or 2.8%. So this is like, I don't know how to put it to you. This is like, I guess us old people are skeptical because we've had our illusions shattered. I have this illusion shattered that if you give me a square meter, I can make a ton of power, and it's not true. And so we are a little bit in love with solar panels because we think in our mind that they're a great solution. 35% efficiency, but they're not. They're 2 or 3% efficient. And that's when everything is working. So that's to keep in mind. Another, which is you're going to need a ton of area. If you have a satellite that needs real power, you're going to need a ton of area. So, okay, going on to slide 4. This goes back to my little prelude to the whole thing. You can say to yourself, oh, I'm just a power engineer. But what you decide as a power engineer is going to impact everybody else, right? Because as a general rule, the batteries are the heaviest single element on the satellite. Therefore, what you decide to do in terms of the power budget and the savings that you as a power engineer are going to try to affect by negotiating with the processor. This mission to the moon, man, it's really frustrating. They have a microprocessor, which they picked, which is a space-qualified microprocessor. Space-qualified microprocessors are notoriously big power consumers. 22 watts to keep just the microprocessor chip, that little, highly integrated chip, running 22 watts. That's an impressive number. And, it's half of their power budget. And I was like, really? For a 2-week mission on the moon, we have to go with this megarad qualified, processor that would be adequate for a polar orbiting satellite that would be in polar orbit like GPS. Can't we just buy, an Arduino and, that will consume a watt? no, well, okay, I'm not going to, I don't want to be the bad guy who says, I think this is a waste of, of money, of time, of power, and it's driving. To me, the greater risk on that mission is they're going to freeze to death. It's super cold up there, particularly when they're get in the shadow of a rock. And they're at the polar South Pole, at the South Pole of the moon. And they're going there on a date when the South Pole of the moon, where they are, will have 2 weeks of sun, and the mission is going to last for those 2 weeks. When it's over, they freeze to death, and that's the end of the mission. In the meantime, they can freeze to death because they occasionally crawl into a crater or they get behind a rock and the sun they're in shade. At that point, they have to wait it out. So they have to turn on heaters, and that consumes a lot of the battery power. And part of those heaters are just keeping the batteries warm. It's a tough go to spend a couple of hours. They go through a lot. And I'm like, okay, let's get rid of the 22-watt processor and invest in more heaters because I don't want to freeze to death. No, we can't live with, the single event upsets and blah, blah, blah. But I understand the moon is a bad radiation environment, but, there wasn't an understanding on the part of the team that by being ultra safe on radiation, they're being ultra risky on thermal. So, my point of all that being the power affects everything. Because the power affects the choice of the processor. The power affects how much redundancy you can carry. The power affects the radio antenna size, because you're going to be saying, I can't afford a transmitter of 10 watts. I can afford a transmitter of 1 watt. The power determines the deployables. Usually, if you have any deployable at all, it's a deployable solar panel. How are we going to deploy it? What's that going to do to the mass moment of inertia? Is that going to generate gravity gradient disturbance torques, solar pressure disturbance torques? So the power guy is affecting the attitude control people in a big way, because they also affect where the center of gravity is. Then the whole mechanical layout revolves around, where do we put these batteries, because they're so heavy, right? Of course, the thermal, because the more power you need inside the satellite, virtually all the power you create is dissipated as heat. The only power that actually leaves the satellite is in the radio output in the radio output. All the rest of it is dissipated inside. And what are you going to do with all that heat? So the more solar panels you put out there, the more you have to worry about, how am I going to get rid of the heat? So, then you've got it, it kind of goes on and on and on, right? So, because if you want to get high efficiency, you're going to have high efficiency power regulation devices. Those are digital devices which are subject to radiation. They can have bit flips, they can have latch ups. Then you've got to have watchdog timers, and pretty much you look at all those electronics in the guts of a satellite, a lot of it has to do, look, the electric car is the same way. Everybody talks about the batteries, but the electronics controlling those batteries is a huge cost element for those cars. And as the price of batteries goes down, management of high current, high powered, analog electricity has not followed, the digital world in terms of, it's the same thing in radios, in terms of shrinking and less power required and better, blah, blah, blah. That's true in the digital world, where you're moving bits around and bits have no mass, and an infinitesimal amount of power. Here we're talking about amps, and amps are amps. And so, you cannot pass an amp, unless you get to superconductors, through a wire has to be a certain thickness. The power dissipation with any given efficiency is going to be some fraction of, that 10 kilowatts that you're generating on that big satellite. So the power affects everybody. And that's why I think, every engineer should be a systems engineer. So these are some pictures of, of satellites and how the power drove the system design of the satellite. This was HEDI, a satellite that my company built for NASA, but our scientific customer was MIT, and worked a lot of years of my life on this satellite. And it was kind of a tragic story. You see it mounted on a rocket. This was Pegasus. And we actually had 2 satellites mounted on the Pegasus. That satellite was then enclosed in a cylindrical carbon composite, trash can. And the top of that trash can mounted another satellite, which was built in Argentina to do solar research. HEDI was looking for high energy transients. That was the high energy transient experiment was HEDI. And it was looking for, gamma ray bursts. Gamma ray bursts happen fairly often, but we're not usually looking at them. And we wanted to see them through the UV, through the visible, through soft X-rays, a broad spectrum instrument that would look at half the sky and the half of the sky that is not pointing at the sun. So we pointed the satellite at the sun. And those solar panels, of course, had to be deployed. And so you can kind of see that was the only deployable we had, and it's 4 big deployables. The tragic story of that is a reliability problem all of its own, but there were several launch delays, in a nutshell, several launch delays, and not, thank goodness, not due to us, and due to many other factors, not due to the Argentinians either. There had been problems on a previous launch of the same rocket. All the rockets were frozen for a while, and while they worked it out and made modifications and so on, when they got into space, they didn't have enough power in the rocket to separate the 2 satellites from the rocket, because they have these pyrotechnic bolts. They need several amps at several volts, and just the batteries, that non-rechargeable batteries, had aged out, and there was no power. And so we remained forever inside of that trash can, and we had power in our own batteries, but we couldn't recharge the batteries because we were enclosed in this trash can. And our satellite was talking to us, saying, it's very dark out here. Can we do something about the fact that it was very tragic. We were receiving the satellite. It was working inside that can for about a day, slowly running its batteries down. We knew that it would, it's very tough. We worked, that was a 5-year project with a lot of blood, sweat, and tears, a lot of arguments with NASA over budget, a lot of breaking new ground because a low-cost, high-risk mission like that was a new thing to NASA. And then to have it not work for an idiocy like that was really tough. Then we mounted a two-year campaign to get NASA to fund it again, which they did, and it flew. And they made the first discovery in real time of a gamma ray burst, and it was published in Science. It was a huge victory, but by that time that huge victory came, all of us but the scientists had long ago moved on. So, it was better than not, but it wasn't a great story. And all hinged on power. That was basically what it was all about, that these batteries had run down, so there was a power problem. And then our batteries ran down because we had a different power problem. Power, is everything. So in a sense, especially if you're a power person. Okay, the thing that's interesting about power is it's very easy to want more of it. We're going from, as Jim had always said, it used to be enough to fly by something and measure some temperature and radiation, get a bunch of scalars. Then it wasn't good enough. We had to have pictures. Pictures weren't good enough. Then we had to have videos. Videos aren't good enough. Now we have to have robots on the surface. And every time you do that, the bandwidth requirement multiplies by 10 to 100 to 1,000. That's fine, but the radio power is proportional to the bandwidth. Every bit needs a certain amount of energy. If you want to have 1,000 times more bits, you need to have 1,000 times more energy. And satellite operators who want to broadcast, like Starlink, like the geosynchronous guys, they want to cover all of Canada, all of North America, all of, the Pacific Basin, et cetera, et cetera. The wider you transmit, the more area. You need a certain number of, nanowatts per square meter for your signal to be detectable on the ground by a cell phone or whatever it is. So if you want a wide area satellite, 5 times the area is 5 times the power. It's very easy to multiply the power requirements by 100 just by changing the payload. On the other hand, the supply of power is the sun, and it's not multiplying itself by 100. And solar photovoltaic efficiency is not multiplying itself by 100. And lithium batteries are not going to become 100 times lighter. And, how much can we save in all the other inefficiencies? A few percent. So we can make progress in power. Incremental, 5% progress. But it's not a factor of 10 or a factor of 1,000. The only factor of 10 to 1,000 is the one I showed on page 2. Learning how to deploy exceedingly large arrays in space. And by exceedingly large, I mean 20 meters long. Space, as someone once said, is big. Who cares? If it's 20 meters long or it's 200 meters long, as long as it works, who cares? So in a way, we have to get over our fixation on fixed, dimension solar panels that have to fit in the launch envelope, because it's really limiting us. And the imagination of the payload people is way out there. They'd like to do much higher power things. And we're doing things the way we did them in 1960. So, that's one of those many things that you wonder, isn't the world a little bit smaller than that? I put in red at the bottom small ground station antennas. If you remember, people used to have satellite TV on their roof, and those dishes were gigantic. They were the size of the roof. And a very interesting trade study came out of Hughes, where they said, okay, how many clients do we have? 35 million, right? If we saved each of those clients $100 because they had a small antenna instead of a big antenna, actually the number was more than like $1,000. Let's say it's $1,000. Putting a 6-meter dish on your roof costs much more than $1,000, right? So let's say we want to go to those little, small geosynchronous antennas that you can buy, online or at an electronics store. They're typically 18 inches, little semi-parabola, 18 by 12 or something like that. And we call that sort of direct broadcast. Okay, 35 million people times $1,000 savings of each is $35 billion in savings for the client base. How much more would it cost us to build a satellite with a lot more power so that it could have an adequately strong signal in a very small antenna? And the answer was not $35 billion. So the net cost to society is lower if you have much more power on the satellite and you make much less requirements on the users. If you're in the broadcast business, one to multiple, one satellite serving 35 million, a lot of lessons were learned serving 35 million users, and that was one of them. Okay, going on to slide 6. This is going to be my last slide, because we've already talked about this slide. We saw it on one of the first 2 days of class. And it's only to say that what I said a long time ago, so I thought I'd wrap up with this because we already said it. Small satellites are not particularly limited by power because they don't have much inside of them. Big satellites are limited by surface area because their volume has grown much faster. And so the thing that I said way back in January, a big satellite will tend to have deployable solar panels, a CubeSat will not, because a CubeSat simply doesn't have, there's many other subtle reasons also. CubeSats are cheap, so we don't tend to worry about buying a mil-spec qualified processor that's going to burn up 22 watts just to download bits from a camera and send a 9600 baud signal. Even Arduino will do that just fine on 100 milliwatts. So, these smaller missions tend to be more informal, and so we do more advanced things. That's what attracted me to it. Hey, we can use the latest technology. Whereas if you're working on, a $1 billion program, which was typical of when I was working, in the big aerospace industry, you can't do that. You've got to use things that have been proven, that have heritage, that have been around for 20 years. If you think about the power budget of a laptop computer 20 years ago, it was pretty bad. It was pretty bad news, and that's why they lasted on a battery like an hour and a half. Okay, so that applies to batteries as well. Big satellites, like I once said, my company built a tiny little satellite. It was the first satellite in the world to have a lithium-ion rechargeable battery. I mean, how is that possible that a company, at the time we had less than 50 employees, in an office park in Herndon, Virginia, flew, with a bunch of people like me running it, young people. I was young at the time anyway. We were not NASA. We were not, Lockheed. We were just Aeroastro. Nobody had even heard of us. And yet we flew the most advanced power system ever flown in space. Not because those people aren't smart, but because there are so many constraints on big missions that it's the small missions that you really get to do the wild and crazy stuff. And I love that stuff. So, I wanted to work in that area. Okay, so that's my wrap up for this part of power. That's 6 slides. out of a lot. So there's gonna be at least 2 more. Okay, gonna go back to picking up my phone, and I'll get back to you with version number 2. Bye bye.